I'm going to be talking about stream processing today. And I've got a lot of stuff I'm going to try to cram into 30 minutes. So just as kind of a disclaimer slash shameless plug up front here, there is much better coverage of these topics in the last chapter of the book that I'm writing with Runar, Functional Programming in Scala. And the book also does a much better job than I can do here in 30 minutes, just introducing all the things that I'm going to build on here and all the stuff that you need in order to get to this point. So, and I encourage you to check it out. And the book is actually half off today if you use this discount code, which I will flash up again at the end. So, with that said, let's get rocking here. So, we are going to start by looking at what is called a single input stream processor. And it's this type Process1. And it defines, so Process1 I/O, it defines a transformation from a stream of I values to a stream of O values, where a stream is defined like more broadly. It could be an in-memory Scala stream, or it could be a stream of rows coming from a database, a stream of HTTP requests, a stream of lines coming from a file, etc. So it takes the form of a state machine that can be in one of three possible states. So it can be in the halt state. So this signals that the transformation is done emitting values to the output stream and reading values from the input stream, and the transformation is finished. It can be in the state of emitting values to the output stream, in which case we have this sequence of O values that should be emitted to the output, and then tail, which defines the next state to transition to after those values have been emitted. And finally, there's an await state, which indicates that the transformation needs to read a value from the input stream. And then when it gets back an I, it's going to use this receive function to transition to the next state. And if the input stream is exhausted, there's no more elements left in the input stream, then we transition to the fallback state. Okay? So pretty simple. So let's look at a typical definition. Line wrapping is a little bit mangled, but so this is a process that's going to compute a running sum of all the values that it's seen so far. And you can see we're just in a loop. We're going to await, so read a value, a double from the input stream, and then we're going to emit that value added to the current accumulated total. And then we're going to recurse or repeat. Our next state we'll just call go again with the new accumulated total. And if we were sort of to apply this to an in-memory Scala stream, we'd get the running total of the values that we've seen so far. Pretty simple. So let's look at how we actually write a driver or an interpreter for one of these processors. So it's a state machine, and it's a state machine where it can issue one of three possible instructions: halt, await, or emit. So this is a simple function that interprets those instructions in order to actually transform a stream, an in-memory stream of I, to another stream of O. And you can see this is pretty simple. If the state machine says halt, we return the empty stream. If the state machine says read from the input, then we attempt to do so. If that fails, we transition to the fallback state. And if the state machine says emit values to the output stream, then we do so and then transition to the next state. Okay? So let's look at some operations that are defined for a process. So we can think of a process a little bit like we think of a list, in the sense that the process is going to eventually emit a sequence of O values. And so a lot of the operations that we're used to from working with lists are also defined for process. For instance, we can concatenate two processes together. Run the first process. When it halts, run the second process. We can flat map over a process's output. We can map over a process's output. And there's lots of other functions that we can define. Repeat. This is run a process until it halts, then run it again until it halts, and so on until the end of time, or until the input runs out of elements. We can define filter, take while, drop while. Pretty much any list function that you could define that operates in a single pass over its input you could define that as a process. Okay. So on the other hand, a process behaves a little bit like a function from I to O, or there's analogous operations that are defined for process. So we can lift any function from I to O to be a process. So you can see the way it's defined. We await, get back the I, then we emit the function applied to that I, and then we repeat. This is making use of that repeat combinator that I showed before. And we're just going to keep doing that until the input stream runs out of elements. So another operation that we can define is composition. So just like we can compose functions, we can compose processes. So this is, given a process I/O, we're going to feed the output of one process in as the input of the second process. And the way that this operation is defined is that these two stages are actually going to sort of fuse together, so that as soon as values are emitted by the first stage of the composition, they're going to be immediately, that chunk will be immediately consumed by the second stage of the process. So using this, we can actually define these pretty complex pipelines of transformations. So here's a line counting process that we're first going to filter out any commented lines and any blank lines. We're then going to map any remaining lines to the number 1. We're going to sum it, and then finally convert back to an int at the end. And this is all going to sort of fuse together as if we had written this as one big monolithic loop. Pretty much as soon as values are emitted by the filter, they're going to be consumed by the next stage and so forth. And this is actually, I mean, this is a nice little programming model. We're getting to assemble these complex loops from simpler pieces and still get the same overall efficiency as if we had written things in a more monolithic way. Okay? So that's general idea of a stream processor. Now, this little data type that we've built up so far, it's a little bit limited. So we can only define these pure linear sequences of transformations, right? So we don't really have a way of talking to an external data source like a file. So that's not a file, a stream of lines from a file is not represented in a first-class way in this little API yet. And you know, we're also, constrained to these linear sequences of transformations. Really what we'd like to be able to do is construct pretty much an arbitrary network of these processes where we can fork things off, broadcast the same signal to multiple processes and have them all maybe process in parallel. I want to be able to, of course, read from external sources like files and so forth. I want to be able to write to files. I want to be able to do all these things, and our current process type is a little too limited. So let's think about how we could generalize it. All right, so just as motivation, let's look at the await case of process. So you can see it has this receive function, and receive is expecting an I. So what this await case is implicitly assuming is that there is some context, a stream, which is going to be providing us with I values. Okay? So we're kind of hard coding what the context is. We're saying the context is always going to be a stream of I's, a single stream of I's. So if we want to generalize this, we need to abstract over the context. So here's how we can do that. So I've changed the await constructor. So now it's parameterized on this type constructor f. And you can think of f as the request type. It controls what are the types of requests that this stream processor can make. And for any request that it can make, f of a, somebody else is going to be responsible for evaluating that f of a, giving me an a, and then calling the receive function to transition to the next state. So these two a's, of course, have to agree. And then the other stuff here is the same. We still have this fallback case. I did add this on error case, which, so a process could actually terminate in one of two ways. One is if the input is exhausted normally, and the other is if the input is exhausted with an exception. And that's this is important for ensuring resource safety, making sure file handles gets closed, and so forth. Although I'm not going to really talk about that too much today. So here's the full process type. The await case is really the only one that's changed. The others are just propagating through that additional type constructor. So first of all, let's notice that a lot of the operations that we've already defined for process are going to work exactly the same. So we can still concatenate two processes, these generalized processes. Run the first, when it halts, run the second. That still works the same. Same deal with flat map and map. Repeat. So that's good. Now let's look at how we can actually encode a process 1 as a process. Now, the way that this is encoded in Scala is somewhat interesting. What we're basically doing is we're going to construct an F, that type constructor F, which only allows us to make requests for values of type I. And here's one way you can do that in Scala. We introduce this class isI, and inside of the isI class, there is a type F, but you can see the only constructor that exists is the one that instantiates F with I. So if I have a process isI hash F, then I'm basically saying this is a process that can only request values of type I. So if we look at sort of a call to await, we're going to say await, get me an integer, and then the integer that we get back, that type integer has to agree with the type of the input to this function. So if you're not following this exactly, it's not too important, but I guess the takeaway here is that we're able to construct an F that constrains the type of requests that we can make. And in this case, we're just saying we can only request values of type I. Okay, so now that we have this representation of process 1, we can go ahead and define our compose operation that we defined before. Except this is now that type alias that I just introduced in the last slide. But other than that, the definition is going to work exactly the same way. Okay. So now that we've sort of used that trick, well, we could craft an environment which allows us to make requests from one of two possible input streams. So this is a sort of a request type that allows us to request a value from the left, which is going to have type I, or request a value from the right, which is going to have type I2. And we're going to call this a T because, the shape of the letter T, it's sort of combining together sort of two different things into one. And we can just define this as a nice little type alias. So this is a process which could make requests from one of two possible input streams. All right, so let's use this to define zipWith. So zipWith is a T, and let's look at its definition. We await L. So this await L is just a little convenience function that's going to call await, passing in that L request value. So we're going to await from the left, we get back an O, await from the right, get back an O2, and then we're going to emit the function applied to those two values that we just received. And then we're going to repeat. Okay? Pretty simple. And then we can also define a function on process T, which is going to take one process, another process, and a T, and then feed the output of those two processes to the T that you just defined. So you can use that in conjunction with the zipWith to zip together processes, merge them. So notice there's nothing about T that requires that we read one from the one source and then read from the other source. We could read 50 values from one source, then 3 values from the other. We could interleave the two sources in whatever way we want. So we have a lot of flexibility there. Okay, so let's look at how we can represent effectful sources like the lines of a file or a stream of HTTP requests or a stream of rows coming from a database. So it turns out that if we just let the F type of our process be some monad, like let's just pick I/O, the I/O monad, then you can think of that as a source of values. So I'm going to explain how this works. So let's look at the await case. So here I've just substituted I've substituted an I/O for the request type. But you could also imagine maybe future A. So let's think about if we're writing a driver and we encounter an await case, we're going to have an I/O action or a future. And then we're going to have essentially a callback to transition to the next state once we've evaluated that future. So all we need to do is just evaluate this or run the computation, and then when we have the A, we go ahead and call the next state. And of course, this could be using actual non-blocking I/O primitives behind the scenes, using futures. And so we don't necessarily need to be occupying a thread and so forth. So it actually turns out that we don't even need to be able to run the computation. We don't need to be able to run the request type. We just need to be able to flat map into it. So we just need it to be a monad. And we need a little bit more than a monad because it needs to be some context where we can catch exceptions and throw them. But it's essentially a monad. When the state machine says await, we just flat map into the request, and then we now have the value, the result, and then we transition to the next state. And we can define this function collect, for instance, which given a process FO and a monad, it's going to return an F of all the values that were emitted by that process. So this is kind of the end of the universe. Okay, run your entire process and get back its list of results. Okay, so let's look at some examples of using this. So we could create a process which is backed by the lines of a file. It's a process IO string. And then we can transform that as if it were any other input stream. We can compose it with other things, filter it, map it. We can then pull in another file as we go. Let's look at another example. The rows of a database given a prepared statement. We can get a stream that is the output of all the rows of that query, running that query. And then more generally, we can define this resource-safe combinator here, resource, which is going to build some stream from a resource which needs to be allocated and then cleaned up when the resource is done. So for instance, this could be a file. You need to open the file at the start, so you need to acquire a file handle. And then you need to make sure you close the file when you're done, either if an exception occurs or if you just are done processing. So now we can read from effectful sources like files, streams of HTTP requests, and so forth. So what about writing to files, or writing HTTP responses, or writing to a database? So it turns out this is kind of a somewhat surprising thing, but we can think of a sink as a source of functions. So a sink FO is a source of functions, except they're not pure functions, they're effectful functions. So it's a function that's going to return F of unit. So let's think about how this would work. Let's say we had file in, which is a process IO string. Let's say it's the lines of a file. And then we have a file out, which is a process that is functions from string to IO unit. So if we were to just zip these two together using our existing combinators, we get the line and we could get the function, and now we can apply the function to the line, and we get back what? A process IO unit, right? Because we get all the IO units that are produced by that file writing process. So how do we actually run all those IO actions? Well, it turns out there's this function that you can define, eval, which you can actually define for any F type. It doesn't care. And all we're going to do, so this is the relevant case here, is right before we emit a value in the process, we're going to await to basically request that the driver evaluate that action. And then when we have the result of that action, we're then going to emit that. So let's now use this so we can even generalize it a little bit further. Our sinks don't need to just return unit. They can actually return a value. So we can define this type channel, which is an effectful transformation between I and O. And you can see it's just a source of functions from I to f of O. So using this and this function 2, we can define, this is like a little example here, read the lines from this file, filter out any comments, map over the lines of the file, converting Fahrenheit to Celsius, and dump that to Celsius.txt. And this is all going to happen incrementally, possibly even using non-blocking I/O primitives. And we're not going to load the entire file into memory. And we're also assured that the file is going to be closed in the event of exceptions or if things terminate normally. So this is pretty awesome. So we've so far constructed a little library that lets us describe these very complicated process networks. It's really an arbitrary graph because since we can send messages or elements in either direction, we can represent both sources and sinks. And we have this branching operation T that lets us sort of connect up two linear pipelines of transformations. We can now pretty much represent an arbitrary graph of things that are happening. Okay, but there's just one problem with what we have so far. So the problem is that we're forced to be completely explicit about the order that the effects are happening throughout the entire network. So to see why this is kind of a problem, let's go back to the zipWith definition from earlier. So there's something kind of arbitrary about this definition. So I'm awaiting from the left and getting back an O, and then I'm awaiting from the right and getting back an R. So I'm explicitly picking an order. I'm saying read from the left and then read from the right. Now, I may want to be that explicit because maybe there's some external effect associated with these requests, and I want them to happen in a particular order. But I may just want to say, hey, request from either the left or the right, I don't really care. Whichever one comes back first, I'll take that one, and then I'm going to make a request for the other one that I didn't get. Okay? So we can represent that sort of non-deterministic choice with a new request type, which is called Y. And so Y now has three cases. We can request an A, we can request a B, or we can request either A or B, I don't care, in which case we're going to be prepared to handle either an I or an I2. Okay? So we can still make the same explicit requests, but now we can also non-deterministically make a request for one side or the other. And again, we'll define a type alias here that just wraps that up in a type Y. Okay, so let's revisit our zipWith example. So now the definition looks a little bit different. So we're going to await AB. Again, that's a little helper function that's just going to call await with the AB as the request. So we're going to await AB, and now we're prepared to accept either an O or an O2. So if we get back an O2, then okay, let's get the O by explicitly requesting from the left side. And if we get back an O, then we explicitly request from the other side. So what this definition is allowing for is the possibility that whatever is interpreting this driver, or whatever is interpreting this process, is free to use parallelism at this point. So at this point, when this request is made, we are allowed to potentially run the two requests in parallel and just race them, and whichever one comes back first, use that. So in order to actually interpret that request that things be done non-deterministically, we require a context that supports non-determinism. And not all contexts do. But so here's an example of how we can represent the ability to make a non-deterministic choice explicitly. So F is a context supporting non-determinism if it has this operation, F of A, which can choose between F of A and F of B. And let's look at it for a specific type, like, say, future. So this is saying, okay, I have these two futures, A and B. Run them both in parallel, race them. Whichever one comes back with a result first, let's say it's A. In that case, then I'm going to return the concrete A that I got, and I'm going to return a residual future for B, because B that may still be running and like ready to dump a B to some variable in the implementation. So either A could win or B could win, in which case we get back a B and a residual future for A. So this data type just gives us the capability of actually interpreting that non-deterministic request. And you can maybe sort of imagine how you would make use of this data type in the implementation of this function y, which is now going to take a process fo, a process fo2, a y, which may non-deterministically make requests from either side, and a strategy or the capability of actually implementing or making use of that non-determinism in the interpreter. Okay, so I'm like breezing through things here. But so now the last thing I'm going to talk about, I'm going to sort of hand wave a little bit. But so we now have the ability to describe these pretty much arbitrary networks of processes. We can fork things off. We can merge multiple input streams. And we can express non-determinism at any point in our network. And that's a very powerful thing. So it seems like it is possible to take a process network and not just run it on a single machine, but actually compile it to a network of actors that communicate via message passing. And these actors could actually live on different machines. And the interesting thing is we have a ton of metadata. So we have all this information about where non-determinism is allowed in our process networks. And we also have all this information about exactly where effects are occurring as well. And so we have, I think, enough information to compile the same process network description to an actual distributed implementation that is still faithful to the semantics of the original single machine description. So this is kind of just an idea at this point, sort of hand waving, but this would be sort of the holy grail of, you could define this really complex process network, test it locally, and then just simply compile it and have it execute concurrently on 50 different machines. So that would be pretty awesome if that were possible, but not implemented yet. Okay, so wrapping up here. So obviously, Runar and I, we've been working together a lot on this stuff for the book. And, but in addition, my coworkers, Dan Dole and Ed Komet, who I don't know if they're in the audience, but they've been working with us on this stuff too. And Ed has this great library in Haskell, the Machines library, which you can check out if you're interested. And there's also a Scala port by Runar and Dan Dole. And lastly, I think we're going to try to, so this library is sort of crystallized enough, I think, that we're going to try to port it to Scala Z at some point soon. It'll probably be a separate like sub-project of Scala Z. But yeah, it should be pretty awesome. And you guys should check it out once that gets released. Hopefully maybe in the next few months we'll at least have something alpha quality that you can check out. And of course, a lot more stuff in the book if you're interested. So yeah, That's all I got. Questions?
So at Precog, in one of our early iterations on our product, we used iter-Ts to serve somewhat the same purpose here. And one of the problems we encountered was that with the overhead of function calls in Scala, that just performance-wise, we couldn't afford to do things on an element-by-element basis. We had to do things at a block level. And yet there are some operations which require you, take a co-group operation or a join operation or something like that, that require you to look at things on an element-by-element level. So how do you go about with machines sort of translating between those two contexts where you need block level operations where you can apply them just purely for performance, and element level operations where the semantics of the operation needs that?
Okay, so I think, yeah, I mean the stuff I'm talking about here is sort of independent of doing chunking, but I mean one thing you can obviously do is you can deal with more coarse-grained requests. So you can request, okay, not just one element, you can request 50 elements at a time. And when you have those 50 elements, you can operate on things explicitly chunked. So that's one way you can eliminate some overhead. But yeah, I mean, I think on some level, you're paying a little bit of a price by having this really compositional API. I mean, if you really need to just write a monolithic loop to get that last, 15, 20% or whatever performance, like.
In Scala, it's actually not 15 or 20%, it's 90%.
Yeah, well, so I guess the thing is there's huge advantages to having a compositional API, and usually that outweighs the disadvantages maybe of some constant factors. But I mean, I think it depends on what you're doing.
It looked like there was an arrow instance for process 1, so I was wondering why T and Y aren't represented as products of processes instead of with special type representations that were shown.
Maybe come talk to me after. But the arrow for the arrow for process 1. So I guess T allows you to be a lot more explicit about the order that things are happening. The general sort of arrow zipping operation, you're not actually specifying whether you're going to do the thing on the left first and then the thing on the right first, or maybe do 50 things on the left first and then 50 things on the right. So T gives you, in general, a lot more flexibility than what kind of an arrowized API could give you.
I kept thinking through the whole first part of the talk, this should map to actors quite naturally in order to execute the whole thing. So I'm glad that you mentioned that. You might be interested in the type channels I worked on to make actors actually adhere more to the model you're describing of explicit input-output types. But there is one thing which is missing in your description, and that is the supervision aspect, which we implement in akka. When an actor fails, that it is not actually the duty of the one doing the wiring or the one having sent the message to handle failure, but the supervisor, because it is not always possible to group that failure code in a convenient location in this sense. So you need the supervising entity above it.
Yeah, so that's something I haven't thought too much about, but yeah, the whole supervisor hierarchies and how does this play into that? I haven't really thought about it, but I think it'd be interesting to see how that maybe could, or things like that could be incorporated into an API like this.